Okay. So this is more going to be some notes to myself about the regularity of holomorphic functions. In particular, what I want to show is if you're holomorphic, if a function is holomorphic, meaning it is complex differentiable, then it is infinitely differentiable, and in fact, it is analytic, meaning that locally there is a power series expansion. Now, there may be direct proofs of this, but the pedagogical way of going about proving this is through Cauchy theorem and Cauchy integral formulas, to which we will derive. And they rely on other tools like the fundamental theorem of calculus for complex analysis and Goursat theorem. And yeah, this is just a very powerful result about simply being complex differentiable, but with all these properties that is not enjoyed usually for real valued functions. So let's begin. So what do we mean by holomorphic, right? So let f be a complex function, meaning that it is a function that takes complex input and complex output. So let's say f from u to c be a complex valued function where u is some, let's just say it's open set in C. Okay. We say that f is complex differentiable at some point in u if this complex derivative exists. So we say f is complex differentiable at some z naught in u if the following limit of this difference quotient exists. If the limit sh goes to 0 of f of z naught plus h minus f of z naught divided by h exists. Okay? And if exists, we denote this value f prime of z naught. So if exists, denote this value f prime of z naught, right? Okay. And we say it is complex differentiable there. The terminology holomorphic is the same thing. So sometimes we shall also say that f is holomorphic as z naught if it is complex differentiable there. Complex differentiable at z naught. Now, some book will insist that you're also holomorphic on an open neighborhood about this point, but right now let's simplify our definition to just to be complex differentiable at that point. Okay? Because what we're going to consider later is not these edge cases. We want to consider functions that are holomorphic on an entire on an open set. So we will also say f is holomorphic on open set U if f is holomorphic at each point in U. Okay, meaning f is complex differentiable at each point in U. At each point in U. Okay. So the regularity property that we want to investigate is if f is holomorphic on this open set U, what can we say about f? And as it turns out, that F enjoys these very extreme regular conditions. Namely, it is going to be smooth, it will be infinitely differentiable at each point, and of course all the derivatives will be continuous because the derivative of their derivatives exists. And in fact, at every point in this open set, F can be expanded as a power series, meaning there is a local power series expansion that actually agrees with F. Now, in real analysis, there are smooth functions, infinitely differentiable functions, but its Taylor series, its power series expansions don't agree with it, so it doesn't have a power series expansion. So analytic function, meaning having power series expansions, don't necessarily always coincide with the concept of being smooth. However, here for complex differentiable functions, if it's holomorphic, then in fact it is both. Okay, and that's what we want to show. All right. So, of course, I'm assuming we already know some complex analysis. This is just a summary of how we can prove this. So, what do we want to show? So, we will show if F is holomorphic on some open set U, then 1, F is in fact smooth, infinitely differentiable on this open set U. Infinitely differentiable on U. Maybe some people write F is C infinity of U. And 2, F has local power series expansion in U. Power series expansion in U. Is there a special notation for being analytic? Is it just C omega? I don't know. Let's see. Let me go check it out. What is the notation? And let tick functions. Let's see the definition. Is there some notation that we can borrow just to look cool? Maybe it's this omega, right? So this is a typical notation. The F is C omega. Some people write that. Okay, so this is the main 2 results that we want to show, these 2 regularity conditions of a holomorphic function. Okay, how do we do this? So here is a rough roadmap. The roadmap will be, first, we will review the fundamental theorem of calculus. So a roadmap is as follows. First, we'll do fundamental theorem of calculus, okay, in which it will tell us that if a function has an antiderivative, here we sometimes call it a primitive, then any closed loop integral, in that domain to which it has antiderivative, it will be 0, right? Then, with that, we will next show Goursat's theorem, Goursat's lemma or Goursat's theorem for triangles. And Goursat's theorem for triangles, we will establish that if you are holomorphic on an open set that contains a triangle and its interior, then the integrals along the boundary of that triangle will be 0. Okay. Then we will use this to establish the existence of antiderivative for a holomorphic function on a open disk. So existence of primitives for holomorphic functions on open disks. This is a rough outline. Then, using this, we can establish Cauchy theorem, which basically says that if you are holomorphic on an open set that contains a closed disk, then the integration along the boundary of that disk will be 0. Okay? And finally, with Cauchy theorem, we will derive the main tool that will prove these two regularity condition, which is the Cauchy integral formulas. And this is a kind of a nice result. It tells us that if we know that the behavior along the boundary, some boundary integral, it will inform us the value of the function in the center and its derivatives. And because it's informing the derivative, it's suggesting that the derivative exists. Cauchy integral formulas. Okay. So using Cauchy integral formulas, this then will easily deduce, or easily in quote, these two other properties, these two regularity conditions. Okay? So this is a rough idea. So this then will give us regularity. Of holomorphic functions. Okay, so this is the general outline. Okay, now, again, this is assuming we already know something about analysis, but we'll fill in the gaps as we go along. Okay, so again, all we're assuming is that our function is just complex differentiable. So that is to say, this derivative exists. Okay. And so let's start. 1. Fundamental theorem of calculus. So this is saying that if you're a function that emits an antiderivative on some open set, then any closed curve in the open set, if you integrate along it, then you will get back 0. So suppose f is a function that emits an antiderivative, or sometimes we call primitive, on U, on some open U. Now what does this mean? This means that there is some function big F on U such that F prime is equal to little f on U. Then, so here's my set U maybe. So at every point, the derivative of big F is equal to little f. Then, for any closed curve, let's start with gamma first. For any curve, gamma in U, joining the points A to B in U. So here is a curve. This is gamma from point A to B. We have the integral over this gamma, this curve, of f of z dz equal to f of b minus f of a. Okay. So this is, fundamental theorem of calculus. If you already have an antiderivative or a primitive, a function that would differentiate to your given function on your set open set U, then evaluating a path integral, a line integral, this is a line integral along gamma, you simply evaluate the difference of the antiderivative at the endpoints. Okay. Now there's some commentary that we need to make. So what do I mean by curve? Because I want to make this, I don't want to consider crazy curves. So by curve, what I mean is it's a piecewise smooth curve. And piecewise smooth, further, I mean that on each piece it is smooth, namely that you can parameterize it by some function whose derivative never vanishes, and its derivative is also continuous. Okay, so by curve here I mean by curve gamma we mean piecewise smooth curve. So it's a piecewise function of smooth curves, and by smooth curve we mean there exists a parameterization some z of t over some closed interval, say a to b to c, such that 1 z prime of t is continuous, and of course to be continuous it exists at the endpoints. At the endpoints we take the one-sided limit. 2 z prime of t is never 0 on AB. Okay, so basically it's smooth. And also because when it's in pieces, when you parameterize, this suggests some kind of orientation. So when you have a piecewise, we want the orientation to be consistent. Okay, so we will demand the orientation to be consistent. So z prime is also going to be pointing in the general same direction. Okay, it will be clear. Okay, so we have this. So how do we prove this? Well, first of all, one might even ask, what does it mean to integrate, a curve like this, right, along a curve? So the derivative of, so the integral of a complex function over this curve, I guess we should also demand that f is continuous, but then because an antiderivative exists, f is automatically continuous because it is a derivative. Well, is that true actually? No, f will be, big F is, okay, so let's just say it's continuous. Okay, because otherwise how am I going to define this integral, right? So suppose f is a continuous function. No big deal. Later we have holomorphic functions, they're all continuous. So f is a continuous function. Okay. So how do we define this integral right here? Well, this line integral is defined to be this particular parameterization. So let's say you have a parameterization a to b. So let's say you have multiple pieces, right? So if you have multiple pieces, then maybe you go from ai to bi, okay, of f of the parameterization zit, zi prime of t dt. So you simply substitute the parameterization and multiply by its derivative. This is chain rule. And you sum over all the pieces. Okay, so this is the definition. Okay, so if gamma is in pieces like this, with each piece is parameterized by zi, then we define this to be this. Okay. Now further, you say, well, here we have a complex value function that depends on a real input on an interval. How do we define this? So we will also recall, we'll define let's say for a function g that is in components u plus iv, the integral of g, so let's say this is a function of t, is some real part of u plus iv of t, like that. Then g of t dt from a to b, we will define it to be just integrating the real and imaginary components separately, like this. So the obvious way of defining these things. Okay, so this fully defines everything. Okay. All right, and piecewise, finitely many pieces. So I don't want to do with infinitely many pieces right now. Okay. So how do we go about proving this, right? So we will just show that suppose this curve has only one piece to demonstrate a point. But the idea is straightforward. It's by chain rule. So proof is a sketch. We'll see how sketchy we can. Let's just say we're doing with one piece. Well, actually, it's we don't really need to do that. So notice, we'll just do it in full. This integral f of z dz is defined to be the sum of the integral over each of these pieces with these parameterization plugged in and the corresponding chain rule, z prime dt, like that. So note we have this. And also note, if we were to compose the antiderivative big F with each parameterization along the curve, like that, this is equal to big F prime zi of t, zi prime of t, right? This is a chain rule. But this further equals to f of zi t, zi prime t. So this is the integrand over here. So the integral of this f of z dz, it's equal to the sum of the pieces ai to bi of, plug this back in here, ddt of f zit dt. And so now this is now, we can think of this as two components, a real and imaginary component, but then each of them is really two separate real integrals. So here, the real version of fundamental theorem of calculus applies. So this turns out to be precisely f of zi bi minus f of zi ai, like that. So basically it becomes a bunch of differences of endpoints evaluated along f. And, well, we should also stipulate that this piecewise curve, the endpoints join up. The pieces join up. So what we'll get is just the final endpoints, the difference of the two endpoints, like that. Okay. So sketch, but it's pretty complete. It's basically this idea, right? Okay, so what does this say? This is saying that if you are continuous function with an antiderivative on your set, then for any curve in that set, the line integral over that curve is just the difference of the antiderivative evaluated endpoints. Okay. So now, what is the immediate consequence of this? So maybe we should want to box this. Oh, it's okay. We don't need to box this. The immediate consequence of this is that, well, if you have antiderivative, then any closed curve, meaning that the endpoints join up, then the line integral will be 0. So a immediate consequence is this. Corollary, or consequence. Okay. If f is continuous on U with a primitive and antiderivative on U, okay, so some f prime is equal to little f, then for any closed curve, so just a curve that joins back up gamma in U, okay, the closed curve integral gamma f of z dz is equal to 0. Okay. Now, without any specification, this closed curve we always want counterclockwise. Okay. So that is our convention. So without specifying, if orientation not specified, of course here it doesn't matter. Then closed curves are always counterclockwise. Okay. All right. So the existence of a primitive means closed curve integral will be 0. That's the result that we get out of another theorem of calculus. Okay. Next step, Goursat's theorem or Goursat's result. For triangles. So this one is very interesting. This one we will establish that if you're holomorphic on an open set, now if we know there's a primitive, then any closed curve we integrate, it will be 0, right? But we're gonna do something slightly different. We're gonna say that if it is holomorphic, okay, so suppose we know further, not just being continuous, if it's holomorphic on an open set U that contains a triangle and its interior, then the integration along the triangle will be 0. So, and we don't even know if whether primitive exists or not, right? So this is just using the fact that it's gonna be just using holomorphic will suffice, and we'll see how this goes. The statement goes as follows. So let f be holomorphic on some open set U. Okay. So again, this just simply means the derivative exists at each point in the set. So if T is a triangle, such that both T and its interior are in U. So interior of T, I will write this I symbol. So it's the inside of that triangle, R in U. Then the closed loop integral along this triangle of f of z dz is equal to 0. So this is kind of interesting. So here's some open set U. It contains some triangle and its interior. Then if I integrate along this triangle T, it will be 0. Okay. So here, we have some f that is equal to the derivative of some other function. Then we know that the closed loop integral, it could be something weird like this. Gamma. Draw better. That this is equal to 0, right? But here we don't know whether it has a primitive, but we know it's holomorphic. Somehow we need to use holomorphic, meaning it's differentiable at each point to do this. We'll do some estimations. Okay. So this is a very classic but beautiful result. The idea is to chop this triangle into smaller and smaller pieces and then estimate the value of this integral and show that this is equal to 0. Okay, so how do we do this? It's a proof. So let's draw this. So again, I'll write out a sketch because you can fill in all the details in words, but the proof is just by drawing some pictures first. So let's say this is our triangle. Okay. Maybe. Okay. This is our T. So the idea is we're going to consider this integral as equal to the sum of 4 smaller integrals, like this. So we're going to bisect each of the sides, that. And so now we have 4 smaller integrals, right? Okay, so what are the 4 ones? So basically this one like that, this one like that, this one like that, this one like that. The internal edges, they all cancel each other out. So we see that if we bisect each of the edges to create these 4 triangles, the integral over this big triangle T is a sum of the 4 smaller triangles. Okay. So let us denote T0 to be this original triangle. Okay. And let's write P0 to be the perimeter. I'll just write P to be the perimeter of this original triangle T. Okay. So after we quadrisect, I guess, quadrisect, not bisect, this T into 4 similar triangles, right? Because these are the same ratios. We see that the integral over this T0, like this, of f of z dz is equal to the sum of 4 pieces of 4 smaller triangles, right? Let's call it T, the stage 1 of the ith one. So maybe this is T1, T1, 2, T1, 3, T1, 4, like that. Okay, f of z dz. Okay. Now, these are 4 different integrals. There are different values. One of them is the largest one. So in particular, it is equal to, so in particular, not equal to, if we were to bound this magnitude, it is less than or equal to 4 times one of them, right? For some T1, which is one of the 4 pieces. So, this is, this, oh, I guess I forgot the magnitude, right? So this is triangle inequality, and just one of the values is the largest one, right? And so it's less than or equal to 4 times the largest one in particular. Okay. So let's figure out what's going on. So maybe we say it is this top one right here. Okay, so the whole thing is T0. So now we are at T1. So now we focus on T1. Okay. Well, what we can do is we can keep playing this game, right? And so we can keep playing this game. Okay. And what we will get is that we're going to get a chain of triangles such that the sum is bounded by that. So repeat this game with quadrisect. Ti and identify Ti plus 1 such that we have this following inequality. So each stage, yeah, it's, we gain an extra power of 4, right? Because we're just estimating on T1 now. So this is Tn f of z. Okay, so now we have a bunch of nested triangles. So here, I guess I meant the interior of these triangles are nested, right? And the interior, this also include the boundary as well. Okay, but so maybe I'll write this. Like that. So some nested triangles. Nested compact triangles. Maybe that will spark some thinking. Okay. Now, these nested triangles, well, because they're compact, what do we have is that there is a point that belongs to everything, right? So that's Bolzano-Weierstrass. So by Bolzano-Weierstrass, there is a point that belongs in all these interior these triangles. So there's gonna be some z naught in all of these. In fact, it's gonna be unique because these shrink. So in fact, this is unique. But this is in all of these closed triangles. The reason why this is unique because we're in R2 and the diameter of these compacts is going to 0. But okay. But by Bolzano-Weierstrass, such a common point exists. Okay. Now, this of course it is in the interior of our triangle T0, and it's also in U, right? So since it is in U, F is holomorphic at z naught. Okay. And what we can do is we can estimate f, i.e. f prime of z naught exists. But what do we mean by exists? Okay, let's see what the consequence of the derivative exists. So this means, okay, the limit as what? As h goes to 0. Maybe I'll write it like this instead. Z goes to z naught. F of z minus f of z naught divided by z minus z naught. It exists, or this limit exists, right? So this is equal to some f prime of z naught, right? But this also means that the limit of z approaches z naught of f of z minus f of z naught divided by z minus z naught minus, okay, minus, so I'll put this minus on top, minus f prime of z naught times z minus z naught is equal to 0. That this function goes to 0. Okay? So, i.e., if I define this function as, say, r, as f of z minus f of z naught minus f prime of z naught, z minus z naught, divided by z minus z naught. This function goes to 0 as z approaches z naught, right? So whatever this function is. So of course, naively it's not defined as z naught, but the behavior as z naught, it is 0, right? As equal to z naught, this limit exists. Okay, so what does this have to do with anything, right? Well, what is RZ, right? So notice, namely, okay, if you solve for this, we see that f of z then is equal to f of z naught. So solving for z. Plus f prime z naught, z minus z naught, plus r of z times z minus z naught. Okay, so this function f of z is equal to this, at least near z naught. And again, this function r of z goes to 0 as z approaches z naught. Okay, so this is really just basic properties of being differentiable, right? You always have this first order approximation like this. Okay, so this all work is just, this is just true what it means to be differentiable. These are consequences of being differentiable, even for real, right? Just consequence of being differentiable at the point z naught. Okay, so we have this linear approximation like this. Okay, so this is saying that, well, when does this turn on, right? Well, as n gets larger and larger, eventually we're going to be near z naught that this turns on. So there comes a point we can apply this approximation. For large enough n, for all large enough n, the magnitude of this original integration along this triangle that we're trying to integrate, f of z dz, is less than or equal to 4 to the n times, you know, the nth stage small triangle, f of z dz. Okay, now eventually we're going to be near z. These triangles are going to be in some open neighborhood about these z naught. Right, so maybe z naught may be here, but then this is all the nested triangles. So this approximation is true in some open neighborhood around z naught, and the triangles are going to be inside the z naught. So for large enough n, okay, the interior of Tn and the closure of the interior of Tn is going to be inside this neighborhood of z naught such that this star approximation is true. So we can plug that in here. F prime of z naught. Now f prime of z, these are just constants, you see. Z minus z naught plus some r of z, z minus z naught dz. Okay. So now, this is the end stage. We will investigate this a little bit. Now, by the way, r can be upgraded to a continuous function, right? Because f is continuous, being differentiable. So even though we may not think that it's defined as z naught, it's 0 at z naught, right? So this r can be upgraded to be continuous. So this is okay. So now what do we do? Well, don't get fooled about these terms. These terms is just a constant plus another constant times z minus z naught. This is just a polynomial in z. This is a linear polynomial in z, right? This is just a degree 1 polynomial in z. Well, degree 1 polynomial have antiderivative. The polynomials always do in the usual way, which has a primitive. In fact, the primitive exists on all of c. So certainly works in Tn. So what can we conclude about this integral? By the fundamental theorem of calculus, this is 0. These terms to evaluate to 0. Okay. So that becomes 0. So that goes away. And now it remains to do this. Well, okay. What we need to do now is to do ML estimates. So this is less than or equal to 4 to the n times times the perimeter of Tn okay, times the largest value of these two things on Tn. So times the supremum of the magnitude of Rz on Tn times the supremum of z minus z naught on Tn, right? So we have this. Well, what do we know about this? Well, we know that as n goes to infinity, this Rz is going to go to 0 because that gets closer and closer to z naught. So we know the behavior of this term. Okay, so this term if we call this, this term will go to 0 as n goes to infinity. Okay. And what about this, right? Perimeter of Tn, well, if you look at the triangles being quadrisected, the perimeter is halved each time, right? At each stage. So this is equal to 1 half to the nth power of the original perimeter. Now what about this? Well, along the perimeter, and where z0 is between, the distance, is certainly no longer than the perimeter itself, right? So that is to say, a point somewhere in or on the triangle to a point in or on the triangle is going to be less than the perimeter of Tn, which equals to, again, 1 over 2 to the n of the original perimeter P. So, conclusion, putting everything together, the original integral over this triangle, f of z dz, is less than or equal to 4 to the n times 1 over 2 to the n times p times some number that will go to 0 as n goes to infinity times another factor of 1 over 2 to the n times p. The 4 to the n and 2 to the n all cancels, and we see that this goes to 0 as n goes to infinity, right? Because it's get closer and closer to z0. Hence, what do we conclude? We conclude that this is equal to 0. Okay. And so this is Goursat's. So what was our hypothesis? Our hypothesis was, if you're holomorphic, to which we use to get this linear approximation of this R function, if you're holomorphic on some open set that contains the interior of a triangle and this triangle, then the closed loop integral along this triangle, it is 0. This is Goursat's. Okay. Next, what we will show is that using Goursat's, we can establish that if you're holomorphic on an open disk, then you have an antiderivative. Okay. So next up, if f is holomorphic, on an open disk, then f has a primitive on that open disk. So let's go to this open disk D. Then f has a primitive on D. And we will do this by Goursat's. Okay, so we'll save this for next time.